when you're graphing on these, when you have r equals 2 cosine theta, it's just really nice to have the polar graphs, which is why I have them to pass out to you for your homework. Just like when you graph with xy's, you can make an xy chart, we can make an r theta chart. Which one should we pick first? Should we pick thetas first and plug them in to find r's, or should we pick r's and plug them in to find theta? I think we should pick theta first because we can just plug theta in and get the r's, right? Remember that we think of it as r theta though, so I don't know how you want to write this. If you want to write thetas first or r's first, I think I'll just write thetas. Theta's your angle. So I'm just going to pick a bunch of the angles here, and then we'll decide how many we need to pick eventually. But I think 0 is a good angle to start with. And this is where you should be able to do this pretty easily without a calculator. If I give you a calculator, there's nothing stopping you from using your calculator if you're terrible with your unit circle. But what is the cosine of 0? 1. And then 1 times 2 is 2. I think we should pick in between there. So I don't know if you want to pick all of these. Pi 6, pi 4, pi 3rds. Pick them all? Let's pick them all. We got nothing better to do with our time. What is the cosine of pi 6? Square root 3 over 2 times 2. What is square root 3? You with me on that? What is the square root 3? Like 1.7 something? Is that right? 1.7? Right, which means it's not going to be on a circle, but it's going to be, you know, kind of get close. What is the cosine of pi fourths? Radical 2 over 2 times 2 just gives you radical 2. And I think, doing a calculator, but I think radical 2 is like 1.41 something. Again, not exactly in a circle. What about pi thirds? Cosine of pi thirds is 1/2, and 1/2 times 2 is 1. Nick, I don't think I have notes for you in the Slacker. You can still Savannah since she's still taking her quiz, because I stole yours again.
Savannah's the automatic one. Oh. That's all good.
No one has to be left out. What about pi halves? What's the cosine of pi halves? 0, 0 times 2, still 0. Here's what's super great about these being trig functions. We still should pick some points over here, but do I already know the values of all the angles, the cosine over here? Because aren't they the same as over here except negative? You with me on that? So I'm going to go ahead and write 2 pi thirds, 3 pi fourths, 5 pi 6, and pi. But I'm not even going to think about them because I know I'm just going to change the signs. Because 2 pi thirds is going to be the same as pi thirds, only it's negative, right? It's going to be -1. Follow me on that? I'm getting this because we're plugging it in up here. 3 pi fourths is now going to be negative square root of 2 or negative 1.4. 5 pi 6 is going to be the same as pi 6, which is negative square root of 3 or negative 1.7. And what's pi going to be? Or we could actually just do pi. What's the cosine of pi? Times 2 gives me -2. Now we could keep going all the way around the circle, but are we just going to keep getting the same r values? Because in quadrant 3, aren't the signs the same as in quadrant 1? Which means you're just going to get the same point. There's no need to graph the same point twice. So once you realize that you've covered all the possible values, you don't have to keep going around the circle. Okay? So let's graph some of these. I know this is a small graph, but you know, you can get the idea in here. If I graph r's and thetas. R is 2, theta is 0. So on the angle 0, I'm going to go to the second circle, and that would be a dot right there, right? At 1.7, on pi 6, I'm at 1.7. So that's a little bit more than half. It's kind of hard to do that on here, but just kind of, you know, do the best you can. Maybe I should be making smaller dots because my dots are gigantic, but that's okay. And then at pi fourths, it's at 1.4, so that should be a dots are getting smaller. And then at pi thirds, it's at 1, so it's like right there on the first circle. And then how do I graph at pi halves? I'm at a radius of 0. Where's that point going to be? Yeah, it's origin, or the pole, also known as. What about the negative one? Remember, what do? How do we graph when the r is negative? So at 2 pi thirds, I'm at negative 1. Yeah, so this is 2 pi thirds 1, so 2 pi thirds negative 1, you have two ways of doing it. You can either add pi to your angle or subtract pi, or you can just flip it over, right? Because that would be adding pi. So instead of being up here, it's actually going to be down there. So this is where graphing those points kind of come in handy. Same thing at 3 pi fourths. 3 pi fourths is negative 1.4. So it actually needs to be down here, right? I need to flip it over from 3 pi fourths, which really should be at 7 pi fourths, because if I added pi, so 1.4, we'll say is about right there. And 5 pi 6 is at negative 1.7, but I need to flip it over. I need to add pi to it, so that's going to be 11 pi 6, and that's going to be, I'm going to say, about right there. And where would the point negative 2 pi be? Is it going to be over here on pi? Do I have that point already? Yeah. And no matter what other angles you pick, if you pick on the unit circle, I mean, you could pick weird ones like 2 pi fifths or something if you wanted to. Do you agree we're just going to keep getting these same points back? Because all of these are going to give me the same values that up here gave me. Positive ones are going to be down here. Like, you're just going to repeat itself, which means if we connect these dots and use smooth lines, not jagged lines, what's this going to make? A circle. Oh, so cute.
So why do we do this?
Because it's fun.
Like, is there like any like occupation scheme that's like, what kind of data is this representing?
Just some cool shapes. There's a lovely stained glass window in your book that has a rose curve on it that, you know, maybe they could use this when they made that glass for the window. Circles, we could graph circles a lot easier than doing this, right? But we could graph, we're going to graph some things like this, like it's going to come out and go like this, and it's going to go like this, and then this side's going to come out like this, and it's going to go like this, and this one's going to come out and go like this. Is there any really use for this? I don't know, but it's cool. This is, those should be all equal, but they're not. This is much harder to graph on an XY plane normally, much easier to graph on this. It's some cool artistic stuff, very much out of my realm, but I don't know. We just do it because it says we're supposed to do it, and that's, you know, that's my job, is to teach you useful information, so I do it well. That's my same answer that I always have. 90% of the stuff you learn in high school, you're really not going to use in your job when you go. Probably 98% of what you learn in high school, you're really not going to use when you graduate. But we do it because we like to make you well-rounded, educated individuals. And many of you are going to change your mind of what you decide to do at some point in your life. And you might actually have to take some more math. Maybe not. Maybe. But someday, you might actually be able to contribute to a conversation because you learned some random useless fact in high school. Or maybe you go on Jeopardy and win some money. Or maybe you're just a nice, well-rounded individual. No, there's some crazy, crazy math. But, like, calculus is what I started with in college, which is the crazy thing, because calculus is the highest math I can teach you here. But calculus is I took calculus as a freshman in college, and then I just took crazy math after that. Like, it just gets crazy. So, linear abstract algebra. That was the craziest class I ever took. That's the class I learned that 1 plus 1 does not always equal 2. And I also learned this joke that I still don't quite get. What's purple and commutes an abelian grape? My professor thought it was hilarious, but I still don't understand it. So, you know.
What did you say?
What's purple and commutes an abelian grape? Someday maybe you'll take this advanced math and you'll learn what that means. Well, here's what it means. An abelian group is a group that commutes, which means it's commutative. So in abelian grape, it's purple and it almost sounds like group. I don't know. I just got that.
So minus 1 plus 1
We don't have time to talk about that right now. We gotta do this.
after.
Modular arithmetic. It's really basically basis, but depends on what mode you're in. It's weird. Mod 1, 1 plus 1 equals 1. Mod 2, 1 plus 1 equals 0. Whoa, mind blown, right? That's what I learned on day 1 of that class, and I went home and told people. So guess what I learned today? Because people are always like, 1 plus 1 equals 2, at least you know that. Nope, changed my mind today. Not always true. You don't take that class. Abstract algebra, intro to abstract algebra was all proof class. Which I just, the whole proofs, the whole test, all proofs all the time. Like, Sam, are you sleeping back there?
I wasn't. If I was sleeping, I wouldn't have woken up.
All right. We did test for symmetry with x's and y's. Same thing with r's and thetas. I don't think this is the most important thing in this chapter, which is why I'm not going to spend a lot of time on it. There's 3 questions on your homework. Stay over it. I just want you to be aware that testing for symmetry could help you with your graph, because if you know it's symmetric and you know what's happening in quadrant 1, right? If you were making a crazy little flower graph and you know that it's symmetric with the line pi halves, aka the y-axis, right? Also known as y-axis. If it's symmetric here and you know this is over here, does that agree you know the exact same thing as over here? That's what symmetry does. So why is it nice to know this? If you know it's symmetric, then you could graph this and you can automatically flip it over without having to pick your points. Do I graph like that? No. So it's why I don't stress this a whole lot, but it's just kind of some good review and makes you do a little bit. Is this going to be a big part of your test? Definitely not. Is it going to be on your test at all? I don't even know. Not sure. So there's a chance that you just have to do it on your homework for me today, and you might not have to do it again. So that's good, right? But to test for symmetry, you want to check that if r theta is on your graph, then the big idea is what has to be over here. And there's 2 ways to write it. One way to write it is to say if you want to leave r positive, then you could say that this becomes theta minus pi. Kind of weird to plug that in. I think the easier one to do is to do the negative r. If you make r negative, then you would also make theta negative. So we could say this is the same as negative r negative theta. And this is what we're going to use in a minute. I just have 2 examples of this, so that's a good thing. I just have 3 of these. We're going to test basically symmetry with the x-axis, the y-axis, and the origin. Only in polar coordinates, we call that the line pi halves. That's the angle pi halves. We're also going to check x-axis symmetry, because that would mean if it's up here, it's down here. That's the next slide. So if it's up here, if this is my r and my theta, and it's symmetric with the x-axis or the polar axis, this one's the one that's the easiest for me to remember because it makes the most sense to me. If this is theta, do you agree if I go this way, it's just negative theta? So this would be r negative theta. I don't even know why I give you both of these, just because the book gives you both. The one that's just the simplest is the one I use, so we're going to circle that one. But if you wanted to make r negative on this one, that's the same as saying negative r pi minus theta. I don't know that that's necessary. That's the easiest one to use, and it makes the most sense to me. So this is like the x-axis. And then the last way we're going to test for symmetry is with the origin, and that's where it like flips from here to here. Some of those rose curves, like the flower petals I just drew, those are going to be symmetric with all 3 of those, which means if you know that, you don't have to make the giant chart. That's why people say you should do symmetry, because you could just test for symmetry and then flip it over and not have to pick a bunch of points like we did on the first problem. So the pole, that's like the origin. That means if there's a point here, then there's a similar point out here. So this one is r and theta. This one, it should make sense. Oh, I gave myself a paper cut. That you could just add or subtract pi to get to this point. So you could do r and like theta plus pi, or pi plus theta. again, we want to substitute in, so that's not so easy to do all the time. If you do the negative on that one, it's r's negative. Think about if you can subtract pi from that. I think this is the easiest one to use for that one. The nice thing is I don't think this is on your test. I'll check for sure before we have the test, which means all you have to do is do this with your notes, and it's easy with your notes because you have all these to look at. But basically, you're just going to check for symmetry. Does it work? And just like when we tested for symmetry way back in like chapter 1 or 2, you don't always have to show the work, but it's a little bit tricky with the trig stuff. Okay, so let's look at that first example here and see if this makes sense to us. The book actually says test for symmetry with the x-axis, the y-axis, and the origin, or the line theta equals pi halves, the polar axis, and the pole. But remember, think about what we're doing. We're replacing r's with negative r's sometimes. We're replacing thetas with negative thetas. So r we do well with. If r's to an even power and we plug a negative in, that means it hasn't really changed, right? But what about trig functions? You have to think about even and odd functions. Do you remember which trig functions are even? Cosine and secant are the only ones that are even, which means sine and everything else, pretty much you're only going to see sine and cosine here. So you might want to write this up there. If you plug in sine of negative theta, remember that it's odd. That means it changes the whole thing to negative. That's the same as saying negative sine of theta, because it's odd. But if you do the same thing to cosine, cosine is even, which means when you plug in a negative angle, you get the exact same value as if you plugged in a positive. So if you plug in a negative theta to cosine, nothing really changes. It's like r squared. And so you have to keep that in mind as you're doing these. Other than that, it's just plugging in. So I'm going to write these out again for you just so you have them here. So we're going to check the line theta equals pi halves. And what are we checking? We're checking that when we replace r and theta with negative r and negative theta, do I get back the same thing, or is it not equal? Like, is there a negative thrown in there that changes things? And you can tell this without actually working it out. I'm going to work it out since it's our notes. I'm going to change. I don't like green. The line theta equals pi halves. So if I replace r with negative r, I'd have negative r squared equals 3 times sine of negative theta. Remember doing this with x and y's? Any big memory of this at all? It was a very long time ago, but we did it. It was on our first semester final exam. Do you agree this side doesn't change? It stays r squared because it's negative r squared. It's just positive r squared. But over here, because sine is actually odd, that's going to change to negative 3 sine of theta. If it was symmetric about this line, I should get back what I started with. Did I get back what I started with? No. So I would say, no, it is not symmetric with the line theta equals pi halves. It could be symmetric with nothing. It could be symmetric with all of them. It could be symmetric with only one. You're just checking it. So it's like three problems in one. But it's not that much work to do. You're going to not show work. I know it. Then we have the polar axis, aka the x-axis. And again, the big thing is just knowing what to plug in. And that's where you can just keep r the same, but change theta to negative. And this is where you can do this in your head. If you keep r the same, but you make theta negative, do I get back the same thing, or is it different? Is that negative theta going to keep it the same, or is it going to make the whole thing negative? So do I get back the same thing? If that was cosine, would I have got back the same thing? Yeah, we would have said yes to it. You follow me on this? This is exciting stuff, right? I'd rather be graphic. The pole, that's the origin. That's where you're going to change r and theta to negative r, positive theta. And this is where we did this with x's and y's. You learned very quickly that you could kind of just tell by looking and you didn't work it out. If I plug in negative r and a positive theta, and am I going to get back what I started with? Yeah, because negative r squared is just going to be r squared, and if I don't change theta, it stays the same. Because I get back what I started with, the answer is yes. If you do your work like this, where it's very organized and I can see you're saying no to this and no to that and yes to this, that is a fine answer. If your work is ridiculous and hard to read and you didn't actually show all your work, maybe you want to tell me the answer. What is this symmetric for? You could say it is symmetric with the pole. Or the origin. If you said the origin, that's okay too. So I don't care which way you give me the answer. Just make sure that you give me an answer. Yes? No? Maybe? Not that bad. It's just, this is the part you got to know, which is right on your notes. So look at the next one. Same idea. I'm going to write out the test for symmetry. You start doing them and see what you think. You got an assignment sheet, Chloe? I think it's just the first 4 on the assignment sheet for tonight.
The first one?
Yeah. Because I broke it up in 2 days. And remember that cosine is even. If this one had been r squared like the last one, we would have got yes to more than just one of these. But because it's just r over there, when you plug a negative r in, it is going to say negative. When you plug negative theta in, cosine is even. So negative theta doesn't really change anything. So you get negative r equals 3 over 2 plus cosine theta, because it's the same as negative theta. That side's negative, this side isn't. So that's a no. See how you don't actually have to work all these out? So you can just kind of tell. So on this one, polar axis, is it going to stay the same or is it going to be different? Because r stays the same, and when we plug in a negative into an even function, it stays the same. So this one would be symmetric with the polar axis. Don't stop there because there could be more than one yes. But this one does not work because r is negative. And if r is negative and cosine is not changing here, the answer is no. So the polar axis would be your answer on that. Honestly, if I was given this on a test, I don't think I would have it memorized which one I was testing, and I would probably just make a graph and then test, then look at the graph to test for symmetry, because to me, making the graph is easier than memorizing all that, which is why I don't make you stress too much about it. Okay, but it's just kind of a good thing to know. Some people like it to graph, and some people don't. So there is one graph on your homework, so I just want you, I'm going to pass you out some polar graph stuff. I'm calling this day 1A, because on the assignment sheet, which I don't even know if I passed out to you, but I have for you, I'm going to pass out to you today. On the assignment sheet, I have day 1 and day 2, and we're actually turning in this to 3 days. So I'm calling this day 1A, which is just the first 4 problems on the assignment sheet. I will tell you that number 3 is a graph. I want you to try number 3, just like the one that we did in class. Pick some points. We will look at it tomorrow, and tomorrow the big focus is graphing. I'm going to give you a polar graph today. I'm actually going to give you 6 polar graphs because tomorrow you have to graph more. You only need 1 of these today. If you want to do the rest of your homework on this, you can. If you want to do your homework on another sheet of paper and just save this with it, I'm okay. If you want to cut it out, tape it on your paper, I'm okay with that too. But just keep this paper because tomorrow I'm going to say use your paper that I gave you yesterday because there's plenty of polar graphs. I don't think so, but I'm going to give it to you right now. I just passed out second hour. But number 3 is a graphing one, but 14, 15, and 18 are just testing for symmetry, just like what we did in class today. So hopefully it won't be that bad. Number 3 is the worst one. Just try it. Here's an assignment sheet. So in case you're behind on homework or you miss a day, and you'll see that 6-5, there's more to 6-5 day 1 that we're finishing tomorrow. There's some terrible jokes at the bottom.
salad dressing